Hello friends, today we are going to discuss one of the important topic, organization of DNA in a cell, chromatin and chromosomes, which are all interrelated. Okay, organization of, that means DNA organization in a cell, organization in a cell, chromatin and chromosomes. We all knew that DNA is a heavy or huge biomolecule, and this huge sized biomolecule has been packed and fits within the nucleus of a eukaryotic cell. How this happens? A much complexly organized, densely packing system is required to achieve this huge, or what we call a cumbersome process. Okay, I'm not going to the DNA structure and DNA types. Okay, we will discuss in some other class. Today we will discuss how this DNA has been organized in such a way that it has been packed within the nucleus. Okay, before that we have to discuss about some basic facts of a DNA. On average, say bDNA, its thickness is 0.34 nanometers. 0.34 nanometers. That means the bDNA. It's the most common form of physiologically active DNA. Its thickness and its molecular weight is 660 daltons. Its molecular weight. Okay. And how the size of the DNA is measured? Base pair composition. That means the measurement of DNA may be measured in terms of base pair composition. Say for instance, 1000 base pairs equal to 1 kilo base pair, and 1000 kilo base pairs equal to 1 mega base pair, and 1000 mega base pairs is equal to 1 giga base pair. Otherwise called, it is 10 to the power of 3 base pairs, 10 to the power of 6 base pairs, and 10 to the power of 9 base pairs. In terms of what we call base pair composition, base pair composition, we measure the size of DNA. Okay, simple. 1000 base pairs equal to 1 kilo base pair, 1000 kilo base pairs equal to 1 mega base pair, and 1000 mega base pair 1 giga base pair. So 10 to the power of 3, 6 and 9 base pairs. That means it depicts upon that DNA is a huge molecule. And how come this huge sized biomolecule has been fit in a nucleus having nearly 10 μm diameter? The nucleus. Okay, that means the size of the DNA is 1000 times higher than the size of the actual size of the nucleus and cell. And how come this has been fit? For example, if it is a cell and this is in this nucleus, and a DNA of this size has been organized and packed within this. So we'll discuss about it. Okay, and most important point in terms of length, what we call contour length. Contour length of DNA. Contour length of DNA is 2 meters. For example, take a eukaryotic cell. That means the total genomic DNA in a cell. If we measure the total genomic DNA in a cell, it is called contour length. It measures 2 meters. And this 2 meter heavy sized DNA biomolecule has been packed neatly within a small cell, say around having 10 μm diameter nucleus. So why I am stressing this point, this shows how better the organization, how better the complexly arranged thing, so that the DNA may fit within this small shape, that is small nucleus. Okay, so it's about some basic facts. Okay, next, how the DNA has been organized, what we call DNA packaging. Okay, within the nucleus. So we have discussed about, I told already, DNA, the chromatin and chromosomes, they are all interrelated topics. How? For example, DNA plus various proteins is called chromatin. This is very important. DNA plus various proteins, for example, history with respect to eukaryotic cell I am saying, okay? And then we'll discuss about prokaryotic cell. In prokaryotic cell is very simple, okay? And first we'll discuss about eukaryotic cell. Eukaryotes. DNA plus chromatin. And this chromatin is thin, uncondensed, loosely organized. Okay? When this become condensed, rod-shaped, highly organized, compact structure, this is called chromosome. For better understanding, a boy of 8 years age is a chromatin. When he crosses the adolescence, he becomes chromosome. That's it. That means for example, a person having 25 years age is a chromosome. 8 years boy is a chromatin. Simple, okay? It becomes chromosome. When, that means depending on the context, we have to use the specific word. That means chromosome, the word we have to use when the cell is dividing. For example, metaphase chromosome is generally the conventional example to describe the structure of chromosome because it has been condensed. Highly organized, rod-shaped, and visible. Of most important, it is visible. That means when the cell is not dividing in resting phase, for example, of course we should not use the word resting phase, okay? When the cell is not dividing, then let us use the word chromatin because chromatin is in the form of thin thread-like structure. When it becomes condensed, use the word chromosome. And what is chromatin? DNA plus various proteins. I told you, they are the integral topics. One have to understand, very important, okay? And another word is called chromatid. This is very important. For now, just listen about this and later onwards we will discuss point by point, okay? Chromatid is nothing but either of the duplicate copy of chromosome. Either of the duplicate copy of the chromosome. That means each half of the chromosome is called chromatid. We knew that in a diploid cell, the chromosomes occurs in pairs. For example, in human beings, we have 23 pairs of chromosomes. We have 23 pairs of chromosomes, okay? And in each pair, for example, say 21st pair, and each half of the chromosome. For example, in each half of the chromosome, okay? For understanding, we'll discuss like this. Later on, we can extend. Each half of the chromosome is chromatid. Each half, that means resultant of longitudinal division of a chromosome is chromatid, okay? So these are some of the basic terms which we have to understand for better understanding, okay? Right. And how the DNA has been organized and leads to these structures. We'll discuss point by point. First, as I told you, DNA, chromatin is nothing but DNA plus various proteins. DNA plus various proteins, okay? First, histones. This is very important. There are different proteins, but major proteins associated with the DNA organization, that means DNA packaging or histone proteins, they are present only in eukaryotes. Prokaryotes won't contain histones. Okay. Histones, actually, there are two sets of H2A, H2B, H3, H4. Present in two, what we call octamer. Okay, say for instance, this is H2A, H2B, H3 and H4. Present in two sets, okay? Two sets. They are called as core proteins, otherwise called histones. The entire concept of DNA packaging rests on the DNA histones, the histone proteins. This is very important. They play an essential role in packaging. How? We'll discuss point by point, okay? First, for example, this is DNA. We knew that. This is DNA. This is minor group. And this is major group. Major group. Okay. We'll wrap around for better understanding. We'll discuss like this. Okay. This is a metaphase chromosome. This is having a size of 1400 nm. This is a metaphase chromosome. Okay. If you zoom, magnify what exactly it is. It contains what I told you, metaphase chromosome, condensed chromosome, condensed one, condensed part. That means I will tell you first. We will explain. That means self-explanatory diagram through. Then we will explain later. This is 700 nanometers. Then, if we magnify this, it will lead to loops. What we call chromosome extensions in loops, but the loops are not condensed. What we call uncondensed loops. Uncondensed loops. This is of 300 nanometers. Okay. Then, if we magnify this, this is very important. It contains nucleosomes, what we call solenoids. Solenoids. This is of 30 nm. 30 nm fiber. Then, if we magnify this, it leads to individual nucleosomes units. Individual nucleosome units. Individual nucleosome units. This is of 10 nm fiber. They are called nucleosomes. And these are solenoids. Then if we magnify this, that leads to naked DNA, this is just 2 nanometers. Naked DNA. So it is a first step, then second, then third, then fourth, then fifth and sixth. That means the point is simple. First, a naked DNA, that means DNA without histone protein, just a naked DNA has been wrapped around, say for example histones, I told you already, histones twice. This is of around 150 base pairs to form nucleosomes. That means say this is a naked DNA of 2 nanometers and this has been wrapped around the histone proteins, what we call core proteins, twice. And the size of the nuclear DNA here is 150 base pair size has been wrapped around, okay. Say for example if these are histones, twice wrapped around 150 base pairs to form the first organizational unit called nucleosome. Nucleosome is a basic brick of chromatin. And this nucleosome further called, actually this is called 10 nanometers. So that means 2 nanometers, then gradually become 10 nanometers. So here carefully we have to understand so that how the complexly organized net, that means DNA has been fit in the nucleus, okay. Then this nucleosome further coiled to become solenoids, which is of 30 nanometers. The first step, the nucleosomes, they further coil. That means here the nucleosomes appears like beads on a string. Take this example, like beads on a string. They are called as beads on a string. Beads on a string of chromatin means nucleosomes have been organized so that the DNA wraps around it. And these beads on a string form further organized, further coiled to form solenoids. Each term contains 6 nucleosomes. This is very important. These are all nucleosomes. and a group of nucleosomes, that means a solenoid structure, and this, and each turn contains 6 nucleosomes. This is 30 nm fiber, and this 30 nm fiber they further organized, further arranged, further organized so that it become 300 nm fiber. How? They are known as SARS, scaffold associated regions. Scaffold associated regions. They are nothing but AT rich regions, adenine thymine rich regions present in 30 nm fiber, are associated with a protein called scaffold, and the scaffold protein, that means anchoring protein, which aids the 30 nm fiber so as to condense, so as to pack further to form a 300 nm fiber. It is called as uncondensed loop structure. They form into loops, solenoid to loop. Then they further condense to form 700 nm structure. Then further can ultimately forming a metaphase chromosome. That's how the issue ends. Say the first 2 nm fiber, then the core proteins plus DNA leads to nucleosome, which are beads on a string, 10 nm fiber, then further coil to form solenoid, which is 30 nm fiber, then further formation of loops, 300 nm fiber, with the help of SARS, that means scaffold associated regions, which are AT, that means adenine thymine regions, and they form the further uncondensed loops called 700 nm fiber, and ultimately chromosome. That's how the DNA has been packed. The 2-meter long DNA has been packed within nucleus. This is very important. So it is with respect to eukaryotes. With respect to prokaryotes, it is very simple. Say for instance, there is a cell, the DNA has been organized in the form of a single chromosome called nucleoid. In case of prokaryotes, here there are no histones, just because of less complexity. DNA has been organized in the form of single chromosome. That's it. That be a double-stranded circle, simply called. And this kind of double-stranded single circle is also present in extra chromosomal plasmid and also in mitochondria and chloroplast of eukaryotes. That means this DNA, highly organized DNA complex organization is with respect to the nuclear DNA, what we call total genomic DNA in a cell, and its contour length is 2 meters. So this is about DNA organization. I told you already, chromatin is nothing but the DNA plus the various proteins. And the organized structure, that means condensed, is called chromosome. Or discuss about different chromosomes and different components. Okay. Then for chromosomes, we all knew that in a diploid cell they occur in pairs. Take for instance, this is a metacentric chromosome. This is a metacentric chromosome. Okay. They are called chromatids. I told you already. Each half of the chromosome is a chromatid. Okay. And this is called centromere. And this is called kinetochore. And this is called telomere. Sometimes they have secondary restrictions and satellites also. For example, there are secondary restrictions. That means secondary constrictions, otherwise called simple constrictions. They are primary constrictions and they are satellites. Secondary constrictions associated with nucleolus. These are spindle fibers. These are spindle fibers. These are spindle fibers. This is a metacentric chromosome. Okay, first we'll discuss the structure, then different types. Chromosome, I told you already, that in duploids it occurs in copies and each of is called chromatid. Its center part, that means called centromere. It is centromere, nothing but special DNA sequences. Specialized DNA sequences. This is very important. Specialized DNA sequences that enables the two chromatids to blend, to link with each other. You know how they link? Because of a specialized DNA sequence called centromere, what we call primary constriction. So primary constriction is very important in attachment of two chromatids, what we call individual half of the chromosome. Then the telomere, this is very important. The last leg of the chromosome. which contains repetitive sequences, repetitive DNA sequences, and it protects the chromosomes from deterioration or fusion with neighboring chromosome. This is very important. So telomere is called, it's just like helmet. And there is one more called secondary construction. It is associated with the nucleolus. That means the ribosomal genes, many copies of genes of ribosomes have been, say, for example, rRNA, say 5S RNA, 5' RNA, and others present in secondary construction through associated with nucleolus. And satellite are some generally identifying markers. Okay, this is the basic structure of chromosome. And depending on the position or the location of centromere, we have different types. Like metacentric is exactly the centromere is present here. And one more important point, kinetochore. This is very important. Kinetochore or disc-shaped protein complex. Disc-shaped protein complex that attaches to the centromere, wherein the spindle fibers attaches to kinetochore so that it can break apart the chromatids. For example, during cell division, we know that this cell will divide. That means each chromosome will break apart. How this done? These are spindle fibers attached to kinetochore and they break apart. So they are called as the kinetochores or act like anchors for the ropes. Ropes are spindle fibers, anchors for the ropes. This is very important. They are protein complex present in the form of disc shaped. Okay. And then depending on the structure, the metacentric here, centromere exactly in the middle, whereas there is submetacentric, somewhat away from the middle, somewhat away in the sense so that one look somewhat longer than others. Submetacentric. Then acrocentric we have acrocentric. They are present at the one end of the chromosome so that the short arm shall become discernible. Their arms, okay? Short arm is discernible. This is acrocentric. Then telocentric we have telocentric chromosome. That means there is no other arm, only single arm is present. It implies that only single arm is present. Okay, so depending on the location of the centromere, there are different cones: metacentric, submetacentric, acro, and telocentric. Okay, then we will discuss about some of the important terms associated with chromosomes. Heterochromatin and euchromatin. That means generally with respect to chromatin organization, heterochromatin and euchromatin. Heterochromatin and euchromatin. Heterochromatin is a dense structure, much condensed rod-shaped structure, which is inactive part. That means transcriptionally it is inactive. Whereas euchromatin is active, loosely organized, whereas thin thread-like, thin part. And when compared to heterochromatin, it is actually the transcription zone. Euchromatin, true chromatin with respect to its transcriptional activity. Heterochromatin is like inert part of the chromatin, the way there is no transcription. In case of mammals, that means in mammals, out of 2 X chromosomes, 1 X chromosome is highly condensed. That means heterochromatin, and they are called as bar bodies, present as a small lobes in the interface nucleus. Okay, they are called as bar bodies. They are nothing but the heterochromatin. Okay, in interface nucleus they are present in case of mammals out of X chromosomes. That means dosage compensation, this concept we will discuss it at some other point. This is very important. Dosage compensation is with respect to mammalian X chromosomes. Okay, then another important point, this is last most important point, that we are called banding pair technique. G banding. For example, this is a chromosome, and which strain is used for banding? This is called Giemsa banding. Actually, this is very important. Dark bands, they are called dark, and they're called light or pale bands. Giemsa, okay? Giemsa banding. This banding enables to identify different chromosomes because different chromosomes have different banding patterns. This is very important. For example, there are 23 pairs of chromosomes and each pair of chromosomes has a specific banding pattern. And where in the dark color, the dark bands are the transcriptional inactive zones. Why it contains dark? Because it contains AT, which this is very important, and inactive. Adenine thymine rich regions in chromosomes are the dark regions and they are transcriptionally inactive. Whereas light bands are the cytosine guanine rich regions and they are transcriptionally active. This is very important. With respect to examination point of view, CSR and others, light bands with respect to G staining contains CG, high rich cytosine guanine region and they are transcriptionally active, whereas dark band, that means Giemsa band, contains adenine thymine, rich adenine thymine regions and transcriptionally inactive. And this banding pattern enables us to identify different chromosomes because it's unique. Each chromosome has a unique pattern. Because the sequence is different. This is very why they are different, because the sequence is different. This is very important. Okay, this is about G banding, and this is about the present class, how the DNA has been organized and how the place chromatin and chromosomes. Okay, I hope you like the class and you make like and subscribe. Thank you.